Okay, welcome everyone to the control seminar, hybrid format, sponsored by Ford and Toyota. So today we are very pleased to welcome one of our former students, Professor Raja Sengupta of the University of California at Berkeley. Raja received his PhD here in the former EE Systems graduate program, preceded the EC graduate program. And I had that was in 1995. And I had the privilege of being Raja's PhD advisor. And at the time, the area of discrete event systems and control engineering was expanding. And Raja wrote a beautiful, elegant dissertation on optimal control of discrete event systems. But at the same time, there was also great interest in intelligent transportation systems. At that time, it was called Intelligent Vehicle Highway Systems, IVHS, a term that was actually coined at the University of Michigan. And Raja was involved in that effort. And when he graduated, he joined the program for advanced technology on the highway, PAT, at Berkeley to continue working on transportation. And then he joined the Department of Civil Engineering as a faculty member, where he is now a professor. Now I'll ask Pete Seiler to talk about the second half of the introduction.
Second half, which was, I was a student at that time when Raja joined in Berkeley, and I believe I might have been your first student. I was co-advised, and I was working on platooning of vehicles, and Raja was interested in communication problems, and that got me interested at that point in what happens if all these cars are communicating, and that was a great time for me to work with you, Raja, and I'm glad that you were able to invite you back. And so we have 3 generations of people here. So with no further ado, we should let Raja go ahead. Thank you.
Thank you very much. Is there a way to dim the light in front?
Yes.
There. Thank you. It's a great pleasure to be here. I mean, many of the people that I learned from and respected are here, and it's still. And I met a bunch of new people today, and Michigan is just as exciting as as it was when I was here. So it's really been a wonderful day. I took a red eye, but I'm feeling fine. It's the conversation, that keeps everything going. So, these days I've been spending a bunch of time on aero. Berkeley's trying to develop a new aero program. We're trying to create a new lab, Aviation Innovation Research Lab, we call it. We're very proud of the URL. And, there's a professor of mechanical engineering who's part of it. Claire's part of it. Mark Hansen, one of my colleagues who works on air traffic management, is part of it. And I'll be okay. So I'm rather interested in this. So I'm not classically an air traffic management guy. I worked on drone control in the DoD space, and then as this drone stuff started to go civilian, I guess I went civilian with it, and now I've sort of become interested in the infrastructure side and the system side of the problem. So there are all these acronyms: UAM, RAM, UTM, and I thought I'd start with those. Right, so this is taken from the FAA website, and it defines UTM. I highlighted this because it says very clearly that UTM is 400 feet. No, it's really the low altitude stuff. They do use the word drone, right? So they are thinking of the small stuff. You can have big drones, but really, I feel like the small stuff is what's in the background. And then this is the other very clear thing that the FAA says that air traffic services, separation services, air traffic services are not provided. So they clearly take drones and put them outside the national airspace system, right? At least in the sense that the FAA controls it. Now, if you go look at the UAM stuff from the FAA, urban air mobility, right? It again says lower altitudes without specifying exactly what, but generally it's higher. And within urban and suburban areas, and it does not say that separation services, air traffic services will not be provided. Right? Though they haven't said it will be provided, they do not say that it will not be provided. And I believe that, that this will be inside the national airspace system, especially if it transports people, because the FAA is politically not in a position to say that they will not provide separation services to aircraft that, if they go wrong, it will endanger people. Right? So that part is important. Why low altitude? This is my sentence, not the FAA's sentence. Because urban suburban trips are short. I put this 10 to 100 mile range. So it doesn't make sense to go up to 30,000 feet if you're doing something like that. Then there's regional air mobility, right? Which is now sort of this mid-distance trips, and 50 to 500 miles, so it's a bit longer. There's some overlap, but the critical part of this regional mobility vision has become sort of this reliance on America's regional airports, right? The UAM people talk about vertiports, right? We'll put these vertiports on top of buildings and aircraft will take off and land from there. Whereas the regional air mobility people talk about, they have this emphasis on local airports. And there's this NASA RAM report that points out sort of these salient facts that, America has 5,000 plus public airports. But the air traffic network has this very peculiar structure, which is becoming even more so because airlines post-COVID have been cutting all the regional routes, right? All these small routes. So 30% of them, of these airports, handle 70% of the traffic, but 60% of America lives within 10 miles of an airport, right? But this also says that, really this is only useful for 50-mile, 80-mile, 100-mile trips, because then you might do a 10-mile leg to your nearest airport, another 10-mile leg out of the airport, and then sort of this mid-mile stuff, right? So why this play, and why does it interest me? Well, this is it sort of started in one way, but my reasons have evolved. So you can see here, this is from the Bureau of Transportation Statistics, that in this 50 to 500 mile segment, the personal vehicle, automobile, is 95.4% of the trips, right? And aviation is just 1.6%, right? And whereas, and if you go, to the 1500 mile plus, right? Aviation is 82% of that, right? This long distance interurban travel. Come to 1000 to 1500, which is also interurban, right? Then aviation is pretty significant. Here, the automobile and aviation are, quite competitive, and even in the 500 to 750 mile segment, the automobile is dominant, right? So this is sort of the picture of American transportation that developed in the 20th century. I mean, this is data from 2019. I try not to use 2020, 2021 data. So, that's sort of the reason that aviation, is the interurban part, and the automobile has been the urban part. In the middle, there's this stuff. So, and, historically, I think, one can sort of understand how this happened, right? Basically, the automobile was well established for shorter trips. I picked sort of 1927 as a date before we started flying commercially, for which I picked 1935 as a date, right? These dates are, of course, a matter of taste because, but, the reason I did that is, basically, it's pretty interesting that, aviation was capitalized. If you look at the Wright company, which was 1/3 owned by the Wright brothers, it was capitalized with $1 million in 1909, which I did I took one of these calculators and inflation adjusted it. It's like creating a company with $500 million today, right? So this is a lot of money. Henry Ford, on the other hand, was capitalized with 28,000, which apparently was all spent by the time the Model A was sold. But then he made a profit selling the Model A and was back in business. And but by the time it was 1927, 15 million of those Model Ts had been sold. And whereas flying, Charles Lindbergh flew in across from New York to Paris, right? And then there was this sort of Lindbergh boom that led to sort of people suddenly wanted to fly commercially. Before that, it was military, right? First World War and all that sort of thing. So the automobile was already there. And so when you look at the did I want to say something else? No. Okay. All right. Yeah. So, the automobile was already there, and this has sort of been the story of the 20th century, right? That the automobile is dominant in the urban mobility market, and aviation's in the interurban mobility market. And now this is a play by technologists for this market that they're not in. And of course, why do they think they can take on this market? Because they basically have a lot of aircraft. Right. So there's, so you can see, so there's the electric vertical takeoff and landing aircraft. And then there are these hydrogen aircraft, right? And these hydrogen powered aircraft people, they talk more about the regional air mobility market, right? That's the market that they want to target. And their approach, I've put two of the leading companies here, Zero Avia and Universal Hydrogen. Universal Hydrogen is basically an Airbus operation, right? The person who founded Universal Hydrogen used to be CTO of Airbus. So what these people take an approach, they take an existing aircraft and they replace the powertrain with a hydrogen fuel cell powertrain. and hydrogen storage tanks. Whereas these electric vertical takeoff and landing people are designing an entire aircraft from scratch. Right, so it's tilt rotor, tilt wing, it's the noise profile, all of that stuff, and they really have this whole vertiport idea in their head. There's a huge amount of design that's gone into, like if they were using a runway in a regional airport, they may not need a lot of the stuff that they've done, right? So this whole vertiport thing is really a very crucial part of their whole makeup, and you can see the difference in capital outlays. Right, so Lilium raised 1.2 billion, Archer 1.5 billion, Joby leads the pack with 1.6 billion, and whereas these people are running at 115 million, 82 million, like that, right? And that I sort of wonder why. I feel some of it is because they're retrofitting; they're just doing the powertrain. Maybe it's that, but I don't understand this stuff well enough to to say that it's exactly that, right? And of course, and I think that if these people succeed in making a significant dent in the urban mobility market, it'll be quite a change, right? It'll be quite a change. I used to think that it'll be, I do think it'll be quite a change for Berkeley, because a lot of these companies, Joby included, are located in the Bay Area. So if these urban air mobility companies get big, like if they take, so I've put here that, look at the size of the automotive companies, right? You come down to number 8 before you reach the scale of Boeing, right? So, this is a much larger business. And if these UAM companies end up taking, I think, even 1/10 of this business, right, then they might become as big as these other aerospace companies, right? And so if actually this industry succeeds, then Berkeley will become the Bay Area will become an aerospace hub, like Toulouse, something like that, right? And I guess with Detroit and Michigan being what it is, there's probably some change here too. I don't know whether this will go down or it'll go up, because these automotive companies, of course, investing in this industry, right? So Hyundai has an air mobility company, General Motors has an air mobility company, Toyota has an air mobility company. So there's all of this. And then, of course, you can see the sort of the difference here, right? And that basically, America flies about 750 billion passenger miles a year, right? But it drives 3 trillion vehicle miles a year. And moreover, and there's also a difference of cost, right? So commercial aviation flies on average at 13.8 cents a seat mile, which actually makes it the most economical mode of transportation in the United States of America. So the Bay Area Rapid Transit operates at about 36, 38 cents a passenger mile. Driving is the rate at which University of Michigan reimburses you if you drive your car on university business, right? So, 60 cents a mile. So, you can see that the whole volume is much greater. What is this urban air mobility business today? Well, here's sort of the Blade example, right? So there's a company called Blade, and they will fly you by helicopter from John F. Kennedy Airport to the Blade Lounge on West 30th. So they got a roof, right? Vertiport. And it's $195, right? So Uber for the same trip is $75. It's a 15-mile trip. They also have another trip from the Hamptons to the same Blade Lounge in Manhattan, and it's $1,000. It's a 100-mile trip, and Uber is $300. I use the fare calculator on the web. Blade revenue is 35 million. And I was trying to get an idea of the scale of flight, right? It's not like I got that 400 flights from Blade. I basically took 35 million, divided by the 300 days, divided it by $195 and came up with this ballpark estimate, right? At 1 passenger per flight. And of course, if you had more passengers on flight, it'd be less than 400 flights, right? But that's kind of the volume of the business today. Okay, now when we look at Joby, it doesn't look like it's going for the Blade business, right? So the way I picked Joby because Joby actually, unlike a lot of the other eVTOL companies, in its SPAC filings, SEC filings, it's published a lot of data about itself. So, but I decided to start here with this paper from Carnegie Mellon, right? Which basically, used some, built a model of the electric powertrain and argues that it's a PNAS paper that argues that if you take a 5-seater Joby aircraft and fill it, right? It's going to be 150 watt hours per passenger mile, right? And a solo electric vehicle, if you're driving, an electric vehicle, right? They vary, but 200 plus watt hours per vehicle mile, right? So of course, if you put 4 people in an electric vehicle, it's going to be much better than this Joby, right? So electric aircraft are still more energy hungry than electric vehicles. But I think this way of putting it says that, if the chancellor got a helicopter to fly around from Berkeley to other places, the students would be up in arms saying, I thought in this campus sustainability was a value, right? But at this level of difference, that may not happen, right? You're not an eco-criminal just because you take an eVTOL aircraft, right? So I think that's important. So the other thing is that, NASA just recently released all this noise testing numbers where, 65 dBA is what they said, that if you're 100 meters, right, 300 feet from a Joby aircraft that's taking off, right, the noise is like a conversation. And to give you, some, 6 dB for, every time you have it. So I put 70 to 80 dBA at 50 feet. And that's about what a highway is, right? So what does this say? It's not like a helicopter, right? And that's been one of the very important things. It's still, I think, noisy because, see, at 100 meters, it's not noisy, right? But where in Ann Arbor would you put a vertiport that has no houses within 100 meters? You could do it in the middle of the Arboretum, right? There's enough 100 meters of clear space, but I don't know what you all would think of saying, let's put a vertiport in the middle of the Arboretum. So I still don't actually think that this achievement solves the whole problem, right? And if you put it on the roof of a building in Ann Arbor, there are other buildings within 100 meters. Right? So what about so I think the whole problem is still there, right? But at the same time, and I feel though, that this whole argument has to be taken on with, okay, we're going to suffer noise, but what do we get in return for it, right? So the Bay Area Rapid Transit is 94 dB when you're sitting on the train. That's awful. But do you think anybody can shut down BART? Nobody can shut down BART, right? It's such a vital part. It creates so much value for everybody that no one can close this thing, right? So I think there's going to be no argument around that. And as transportation colleagues of mine say to me that, fine, Raja, it's technology, it's great, but what problem does it solve? We need to know what problem it solves, right? And then we'll have the willingness to deal with all this stuff. The other thing you can see is that, they really brought the cost down. It's $3 a seat mile is what they say. They say they'll be in business by 2026, which if you look at the same trip, which is $75 with Uber, and 195 blade would be $45 on this Joby aircraft, right? And of course, with the Uber, you can put your whole family in this, right? Whereas here it would outstrip that. But at least, in some ways, one person going, two person going, there's an argument, right? And Uber is used by a lot of people. So I don't think we're talking here about these few people who can pay $1,000 to fly from the Hamptons to Manhattan, right? There are a bunch of interesting numbers, like, they say their aircraft will be able to do 40 flights a day and an average of 24 miles of flight. They think 2.3 passengers per flight. And this is all the kind of thing that they base their $3 a mile on, right? So all this, so this is not like Blade, right? So where exactly can it go? So then, to answer all these questions, we got engaged with NASA and we started building up some tools. And, one of the problems of, sort of running simulations is that so the purpose here was for me to figure out how many people might actually use this thing. What is the total addressable market, right? And so I said that, okay, in terms of, let's just say travel time, right? That you need a travel time benefit in order to be able to use it, then you fall into the total addressable market. Of course, it still depends on price. If I'm somebody who's used to consuming mobility at 60 cents a mile by driving my car, that matters. But I left price out of the whole thing. But in any case, whether you want to do price or you just want to do travel time, UAM is mid-mile air transportation. It's not door-to-door. For Elon Musk, it might be from his door to his office. But when I asked my wife if I can have a vertiport in the front of the house, she said, what about my plants, Raja? Right? So I just don't get this. But anyway, you know, that's the way she put things. So I've assumed that for somebody like me, it's not door to door. It's hub to hub, right? And if it's hub to hub, then to get a travel time benefit, I have to consider the ground traffic leg, the air leg, and then the ground leg, right? So I have to run these simulations together. And, you know, and the scale of ground traffic simulation is much larger than the scale of air traffic simulation, right? So all this has to be put together. So we strung all these tools together. That FE-Cube there is built by NASA. And, you know, you can see a visualization of FE-Cube. It simulates air traffic with congestion. And, you know, you can see all these sort of trajectory variations and all that stuff, right? So, and then, you know, Manta is built by a colleague of mine at Berkeley, Paul Waddell. And it's a GPU fast time simulator. It's really pretty amazing. It'll, you know, take 3 million trips in the Bay Area, which is the morning period that we work with, and it'll simulate, you know, the whole thing in about 5 minutes, right? So we integrated this stuff together and did all this work. The reason you see that business about optimization libraries is how many people can you serve? Well, it depends on how you lay out the vertiports, right? Because that determines, and that's a facility location problem, which is an NP complete problem. So there's a bunch of approximation stuff that we do for it. And then, you know, all that trajectory, deviation, and all those, of course, depends on CDNR, the conflict detection and resolution algorithms, is these aircraft transit airspace. You can see them here. You can see all these deviations. That's because of CDNR as they transit. And then, you know, in order to design the CDNR, when should we use these safe set methods, which Claire Tomlin developed, right? So we use basically her tools and things to do this stuff. We also do, you know, route design. You know, you're looking at that network, and this one, for example, is based on avoiding areas with high population, right? So basically set up a risk, I mean, you know, like areas with low population and low cost, areas with high population and high cost, and then do this using fast marching methods. There's also some, you know, you can also do computation with, you know, of minimum energy routes in wind fields. This is an anisotropic field, so we use an ordered upwind method here. And I have a colleague who works on tropospheric, you know, wind, Tina Chow, and she can give us very, very high fidelity wind data. Like the resolution here is like 5 meters spatially and about 30 seconds temporally. So we can get, you know, really interesting stuff like, you know, I want to fly from here to here, but actually this is the energy optimal path, right? Where you can see you sort of flow with the wind, and then when you have to come in, you actually kind of like, you know, crab in, right? In order to do this stuff. There's also some simple-minded noise, but we don't do that in any sophisticated way. The other interesting thing that, you know, we began to analyze is the availability of airspace, right? So when you think about, you know, this urban air mobility stuff, you want to put it at 1,000 feet, you want to put it at 1,500 feet, 3,000 feet, right? It's obviously going to be important. So, okay, let me put it the way I put it earlier. You cannot put this outside the NAS. You can't say we can do it like UTM outside the National Airspace System. No coordination with, you know, air traffic control doesn't deal with it, because at what is the altitude here? 450. So at 1,500 feet, MSL, if you want to stay out of controlled airspace in the Bay Area, all of this is close to you. These are sort of important points of interest, like the Salesforce Tower, the Palace of the Legion of Honor, et cetera, right? And you can see a lot of them are not reachable, right? This is controlled airspace in the Bay Area. If you assume that you can coordinate with ATC, like, you know, at least like, you know, like general aviation aircraft enter, right? And they coordinate with ATC, and but you stay out of all the temporary flight restrictions in TFR procedures, you have more airspace open, right? And you really get a significant amount of airspace, enough to actually run all this sort of UAM traffic, et cetera, if you can actually, you know, function like an IFR aircraft and be in airport procedures, but only stay out of active airport procedures, in which case dynamically certain sections of airspace are open and close to you, right? And then you get significant airspace. So That's sort of the other thing that we learn. You can of course do this kind of analysis at different altitudes, and we built a tool and all that sort of thing. So what is actually, what people think of as the scale of this problem, right? So, so this was, a report that was published by Uber Elevate, which sort of looked at 3 metro areas and said, we have 1,000 aircraft and we'll divide them up equally. And that was kind of Uber Elevate's estimate, or at least published estimate of what the business was going to be. So I just did the math. I said, every metro has 1,000 divided by 3 aircraft. And I just assumed that they're going to fly 3 trips an hour for 10 hours. Joby has a larger assumption. And doing that, I get, 40,000 people a day per city per day, assuming 4 people per aircraft, or 10,000 flights per region per day. With the Joby numbers, it would be 13,000 flights per day, right? With the same number of aircraft. If Joby put 300 aircraft in a metro area operating under the Joby paradigm, you get 13,000 flights a day, right? So that's the sort of, that's one estimate by a company that, is in this business and was actively looking at it. And so then I started trying to understand that, what does this 10,000 look like? And I tried to take a very minimal sort of approach to it, where I said that, I just want to, I'm going to simulate the Bay Area. And I won't distribute the ODs uniformly, because the urban region is not uniform. I decided to distribute them according to population density. And, so that's how I generate the OD distribution. I said aircraft travel straight lines from O to D, but I put in a definition of conflict, right? Which is based on the distance between 2 aircraft and the heading, right, of the aircraft. And then I said that I'm going to consider that interaction, right? And when are aircraft interacting? But in this case, even if they're interacting, they don't deviate to it. It just flies straight through, okay? So we'll come to the deviation part later. And, I don't know if this is playing. Yes, you can see some green dots floating around. So at, about 1,500 feet, this is what it looks like today. There's 150 flights a day, not much is happening, right? 10,000 look like this. You can see these flashes of red, right? There are these flashes of red when I color an aircraft red when it's interacting with another aircraft, right? When it's in conflict, right? And you can see this is sort of that dense cloud there is actually over San Francisco. It's not over Marin County, right? And so that's what this looks like. And so basically there are, a couple of things that I measure. So I basically look at, the aircraft that are in conflict, and then the number of aircraft that form like a connected component, right? Because I think of this as, this aircraft is in conflict with that aircraft, which is in conflict with that aircraft, which is conflict with that aircraft. And I think fundamentally transportation systems are designed to not allow conflicts between large numbers of vehicles that have to be resolved by the vehicles themselves. So if you think about driving, I think, when a car merges into the highway, there's a 3-vehicle conflict and coordination problem. The moment there's 4, we put a stop sign or we put a traffic light, right? We don't, and of course, computationally, you can understand this problem as, all these mixed integer programming problems that resolve these high numbers of conflicts. It's NP, it's exponential, right? So I don't think you can really execute them in practice, right? So this is the kind of, so at 100,000 flights a day, right? These are sort of different distance measures of conflict. And of course, the bigger the distance in which you consider conflict, the larger the number of conflicts that you get. So we take these cluster sizes and plot this, plot these frequency histograms. And you can see that, at 100,000 flights a day, you get some pretty high dimension clusters, right? They begin to appear. And I'll show you some of the statistics, which will make the point a little more sharply. So this is what 100,000 flights would look like. In the same picture, that big red cloud is over San Francisco. And this is, I feel, what I take away from it. So what I've plotted here is the percentage of time that an aircraft spends in conflict as it's traveling. And you can see that up to about, here's 1,000, here's 10,000, right? This graph is sort of relatively low. And then it has this very rapid climb, right? This is very rapid climb and it takes off, which to me says that at least, this system should be operated in this regime. It should not be operated in that regime, right? So one has to do something to remove that regime, either meter flow and not allow things, or don't allow free flight, structure everything, put them into airways or something like that. And then the other way you can see it is, like I wrote down the 99 percentile statistic of these clusters. You can see it's actually, 0, 2, all that for, pretty long. But it's, when you go from 10,000 to 100,000 is when you start seeing these large numbers emerge, right? So, that's another way of seeing that at about 10,000 is when it starts to take off. And so there is this sort of change in complexity that I think about. And, so at 10,000 flights in the Bay Area, this is the sort of thing that happens. The NAS carries about 45,000 flights per day and about 5,000 aircraft at any given time in the airspace. Now, if we do the same kind of analysis, but this time with CDNR, with conflict detection and resolution algorithms, what will conflict detection and resolution, of course, do? That, when these aircraft, they will no longer just pass through each other, right? They will actually react and change. So what happens when we do this, right? So what happens when we do this is that CDNR now produces a notion of capacity. Because it's trying to preserve separation, right? What it does then is it basically, drops the productivity of the airspace. It drops the productivity of the airspace. It drops the efficiency of the airspace. And if you have looked at sort of these highway models, right? It's kind of like the highway. It's like a 2D equivalent of the highway fundamental diagram. And so you can see that there's this level of flights below which as you push more aircraft in the system, more aircraft are going out. And as you go this way, the outflow actually starts to drop. So there's no reason to operate the airspace here, because you're actually getting less out of it. And also, of course, the number of separation losses also starts to rise very rapidly. And this starts to happen with other measures as well. That, so here we're looking at trip time. So trip time is increasing. So, and we looked at, two CDNR designs here. One is sort of the conventional one, which is direction control. Right, that's how VFR, visual flight rules, aircraft fly. I see an aircraft, we're heading at each other, one turn to the right, right? But these aircraft can hover, so we also consider speed control, and you'll see a difference. Here, there's no difference really. So trip time rises in both cases. One case because aircraft slow down. In the other case, because aircraft are deviating, right? In order to avoid. And again, you see the same thing. Right, it stays kind of like slowly increasing here, and then as you cross that, accumulation begins, and this stuff really begins to shoot up. And then you can observe the same thing in energy. So here there is a difference between speed control and direction control, because in speed control, the aircraft can slow, and it can come down to hover, right? And how much energy will be consumed depends upon the assumption that is made about the hover power. Right, so basically, it turns out that if your hover power is greater than about 1.5 times your cruise power, your optimal cruise power, then this speed control becomes a bad idea, right? That there will be, so this is why the UAM companies, they don't want to hover, right? They okay, and then there are papers in which all this stuff is documented. Here's the power model, as I was showing that if you're you fly at sort of this minimum energy speed, right, and your hover power is up there. There's the different assumptions. Okay, so in summary, I feel that that free flight in the Bay Area has a transition at about 10,000 flights a day, right? Okay, so aircraft flew with minimal interaction up to about 10,000 flights a day, and 99% of the conflicts are 2 aircraft, at most 3 aircraft conflicts, which I think CDNR algorithms can resolve. Above 10,000, interaction rises rapidly. At 100,000, as many as 30 or more aircraft may be simultaneously in conflict. The capacity of a sector today, of an airspace sector today, right? Even today, they have a notion of capacity, right? But the capacity of a sector today is determined by the cognitive capacity of the air traffic controller of the sector, right? And now that, when we're talking about this new regime, though this is not policy, there is sort of a clear belief that the FAA cannot handle UAM and RAM traffic in the same model as it handles a New York San Francisco flight. So New York San Francisco flight transiting today is a very high touch model. The pilot will speak on an average to about 11 air traffic controllers along the way, right? That's a very high touch model. And this class of traffic, since it could be quite large, right? I mean, 10,000 flights in the Bay Area as per Uber estimates, 45,000 in the whole national airspace system. You take 5 major metro areas, you have as many aircraft as are handled in the national airspace system. So if you scale the FAA model linearly, you'd have to double the number of air traffic controllers, right? So it obviously cannot function. It cannot function like that. So if things become autonomous, then actually there won't be this cognitive limit, but CDNR itself will induce another capacity, a free flight capacity, which will limit the risk. It will limit the productivity, limit the flight time and the energy efficiency. The other metric that I never computed, but is important we observe in simulations, is that in direction control, what actually happens is if you take a boundary of airspace, and that's what they're transiting through, in order to do the collision detection and the CDNR, they will deviate sometimes outside that volume of airspace, right, in order to accommodate things. So if there's legacy airspace on the side, this is intrusion into that legacy airspace. And that is an issue, right, that they'll care about. So I actually tend to believe that if that sort of thing is, what will actually happen, even though direction control is preferred, that if the airspace comes to get congested, then the aircraft will actually behave like cars. And they will begin to hover, because you want to protect legacy airspace, they will begin to hover to control risk. And that will, of course, burn a lot of energy and destroy the operating economics of the aircraft. So, you can operate a highway where, without metering, because some people say that why don't we let this whole field work like cars do, right? Unlike flying in the national airspace system, you file a flight plan today if you want to fly tomorrow. Well, I don't file a driving plan before I come to work, right? And in urban mobility, you can't do that. It's not that predictable, right? But at the same time, you can let a highway operate like that. And if it gets overloaded, the cars will just sit there. It'll turn into a parking lot. And if it's an electric car, then there isn't much loss, right? Because the engines just shut off. Here, it's not like that. So I think there's a real problem because you can't operate it like scheduled commercial flights because urban mobility is not like that, but you can't operate it like cars because of the energy problem. And of course, if you, structure the airspace, so we did some analysis as it's not playing, then all this problem becomes very mitigated. Oh, it was playing? Well, you see some red over there, etc. as these things transition. But anyway, let's keep going. It's 4:10. Okay, so 3 trips an hour for 10 hours. This is what I started with. 10,000 flights per region per day, according to the Uber estimate. What does this actually do? What does this actually mean for anybody, right? Well, it certainly means something to the people who are taking it, right? They're saving time, etc. But what does it mean for the rest of us? In transportation, if you want to build things like this, it's a public-private business. You can't just build something this size in the middle of Ann Arbor, right? I mean, the city council will get involved. And then there will be all these questions about, it benefits, these 40,000 people who are flying. But what about the other 250,000 people who live here? What does it do for them? Right? So this thing to me looks I feel this doesn't work. This thing to me looks as big as Grand Central Station. And of course, you can build Grand Central Station, but Grand Central Station serves 750,000 people a day. Right? So, if you look at the Bay Area, has about 4 million jobs in the Bay Area, 400,000 commuters. If you're moving 40,000 people, you're moving 1%, right? And, BART moves about 1/10, right? So you're basically moving 1%. And sometimes you attract the attention of the 99%, right? When you focus on the 1%. And, I'm putting it like a joke. But this is actually a real problem, and all the UAM companies understand this. Like, the ones who feel like Joby that they have the aircraft, they've got the aircraft, that's not the bottleneck, they have the aircraft. The next problem is vertiports, right? So they're trying to meet with the UC Berkeley campus leadership to say, we want to build a vertiport on the Berkeley campus. And so they come and talk to me or my fellow professor about it. And I'm like, I don't break and build concrete. I do research. You have to talk to capital projects. And capital projects wants to talk about shared bikes. They don't want to talk about, they say, what is this thing, right? So this is the whole issue. So should UAM, RAM do more than 1%? Should it do something fundamentally new for us like cars did or rail did? Right. So I went and, I've been looking at housing data, and it's really interesting that, I found this report from the Dallas Fed. If you ever are wondering, what has happened in America over 100 years, look at stuff published by the Fed. Some of that's the repository of America's economic history. And, so there's a report from the Dallas Fed that looks at American housing, urban land value from 1890 to now. And it basically rises pretty regularly at about 1.8% in 1920. Tanks during the First World War. Before that, right? It tanks during the First World War, recovers in the 1920s. Tanks again in the Depression, goes back to 1920s levels. In the Second World War, it gets screwed again. And then 1945 to 1955, there's this very rapid growth. There's like urban land values are rising by 6%, 7% a year. And then 1955 to 1990 looks like this interregnum. America's urban land prices are flat. And then after 1990, it takes off again, right? And if you look at this, it fits with 1956 is when the interstate highway bill was passed by Congress. And 10,000 miles of interstate highway was built in 1960, 20,000 miles in 1965, 30,000 miles in 1970, and 40,000 miles in 1980. Right, and you also see, suburbanization, right? America was about 13% suburban in 1940, and and it's over 50% in 2010, right? So, I started on looking at this because the Wall Street Journal has been observing now for a few months that America is out of land for housing. And at least in the sense of, yes, opening, people promote high density housing and that sort of thing, but at least in the sense of opening new land for housing, it seems to me like the interstate highway system has run its course. We are no longer able to open new land by building interstate highways, because I think the accessibility to the jobs that you would want if you live in that land cannot be delivered by the highway. There's too much utilization of the highway. So the interstate highway and the automobile did do something fundamental for America. We didn't use rail, right, except in New York and maybe another couple of cities. But the interstate highway system did do something very fundamental, I think, for the United States of America. So urban air mobility is this mid-mile air transportation with a non-air first and last mile. So it's actually shared multimodal transportation, right? That's what it is. So the UAM people should actually go and join all the shared bike people and say, I'm also about shared multimodal transportation. I'm also about moving away from solo car driving, right? But they don't. Instead, they went and called themselves air taxi, right? Raising this vision of this door-to-door, service with just me and the thing, right? But they just didn't say that I'm like a shared bike, right? And I of course fell into the same trap. In my NASA analysis, I assumed that the first mile and last mile had to be a car. And then when I presented my work to cities, they said that no, why can't it be transit? Why can't we have bike racks on this stuff, right? So okay, so but this is the kind of stuff that we came up with using all these regional scale simulation tools. We addressed this total addressable market, and I basically simulated just this 2.8 million trips between 5 a.m. and 12 p.m. and then actually focused on seeing the 1.2 million trips between 8 and 9 a.m. how many of them could be benefited by UAM, right? And the reason I did 1.2 million trips is because of a bottleneck in my optimization algorithms. I can't do that many because I try to locate the vertiports to maximize the subset of this 1.2 million that will be benefited by using UAM, right? And then this, of course, gets complicated because whether they'll benefit or not depends on the driving times. But the driving times also actually depends on how many people I'm taking off the road, right? So I have to do all this complicated fixed point computation between the optimization and the simulation to figure all this out. So basically, that's why I couldn't do everything. But anyway, I did this. And this is what we did with NASA. And okay, and then we designed the vertiport network, and so here I'll give you one of the sets of results. So this is here we put in 116 vertiports, right? A very large number, much more than Uber envisaged. 4-passenger aircraft, passengers wait up to 5 minutes to consolidate. I'm trying to increase aircraft occupancy, right? Don't want to treat this like taxi. Each vertiport has separate departure and arrival pads, 120 operations per pad per hour, right? 240 operations an hour total, 116 vertiports located to maximize the total addressable market. We do this stuff and we basically come up with that we can take about 10% of those trips off the road and transfer them to urban air mobility, right? And there's a pretty significant time saving. And we can look at the distance distribution. We of course ran this exercise for 10 vertiports, 30 vertiports, 50 vertiports, 70 vertiports, 100 vertiports, and you can see that when you have small numbers of vertiports, you locate them mainly to capture the people traveling for long distances. Right, and then as you add more vertiports, you can pick up more and more of the shorter distance trips. And we can generate all these numbers that if I have 10 vertiports, depending on how much transfer time for consolidation and all that there is in order to increase aircraft occupancy. If I have large transfer times, I only serve a small number of people. If I have small transfer times, I serve bigger numbers of people. And here 10 vertiports, 20 vertiports, 50 vertiports, 70 vertiports, 100 vertiports is leveling off, right? So that's what it looks like. So above 100 in the Bay Area, it didn't do much, right? So this is sort of why we stopped there. If UAM, so if you can build all the infrastructure that you want, right? And 120 operations per pad, 240 operations an hour is a lot. I think Atlanta, which is the busiest airport in the world, operates at about 100 operations an hour. So I don't think there's any airport in the world that operates at 240 operations an hour. So if you think this is meaningful and you're looking for good control problems, there is a part of this that I seriously want to do. But okay, I'll get to that. If UAM moves 10% of the traffic, it is a significant contributor to urban mobility. That's what the train moves in the Bay Area. At that level of mobility, it will change a lot of things. It will change land values. It will not just help the people who take it, it'll help the people who don't take it, right? Because every time somebody takes the train, they help the people who are driving on the road, right? So, and then a few people will get worse because they're using the roads that lead to the vertiports, which have more congestion, right? And that's a 1%, 2% kind of number. And that's an issue because, equity is very important now. So the other thing to me is that urban air mobility is hub to hub. It's not door to door, right? So I think I don't call it a taxi. Taxi for me is door to door, right? It's hub to hub. So to me, it's not a taxi, it's an Airbus. Okay, so these are my concluding thoughts. So as I said, 10% is a lot. UAM at 10% would change mobility, land values. At 1%, not really, right? There, I think it is vulnerable to this argument. 1% is not the ultra rich. It is not air taxi. I mean, that one, Elon Musk is what, 0.00000 something, right? But it is the, the more time sensitive. Okay, so I would pay $3 a mile for my ride from Detroit to Ann Arbor, right? But if I was going on work, to, because I'm a University of Michigan employee and I'm a professor here and I'm going for a meeting in Detroit with the mayor and I'm traveling on my own budget because at least in Berkeley, the university will not reimburse me for local travel like that. I would not be willing to pay $3 a mile to travel like that, right? So that would be a higher income person than me who'd be willing to do that. So I think at that level, there's this air taxi for the rich kind of criticism, the 99%, the 1%, that kind of thing. And so, the path forward is difficult, right? Okay. The other way I think about it is I said hub to hub, and who builds a 4-seater hub to hub vehicle? Right? That does not make sense to me. And there's another angle from which it doesn't make sense to me. A 4-seater Airbus, to me, that's why the eVTOLs of today look like 1% vehicles, not 10% ones. And here's another reason why. So 2 takeoffs per minute, 2 landings a minute is 4 operations a minute, right? If I'm doing people transport at 2 takeoffs a minute, 5 people per takeoff, 60 minutes, that's 600 people an hour, right? And this is an unprecedented level of operational complexity, right? Which is not seen in today's national airspace system. In a 20-seater, this would be 1 takeoff every 2 minutes, much more, feasible, or 10-seater takeoffs every minute, right? So also, okay, but now if I think about, I think about operational complexity, and I say that I want to focus on the 10-seater taking off every minute, right? A 10-seater electric vertical takeoff and landing from an urban rooftop, that's an Army Chinook is 40 people, I think, right? So a 10-seater helicopter is a big helicopter, right? I'm a civil engineering department, but I'm not a structural engineer. So I did consult a group of structural engineers and I said, this building roof, right? Is it built for excitation with 1-ton aircraft? And they said, yes. I mean, they said, look, Raj, I mean, this is a building. Because there's earthquakes. They said, no, you might have to put some, padding, some, dampening stuff to spread the load and the shock a bit, but a 1-ton load on a roof is not a big deal. So, right, but a 10-seater, okay, so that's another thing. So on the other hand, so you can see how I'm thinking about this. And urban, you see, I'm thinking about it if it's, you talk about this eVTOL stuff and people say, what about the noise? What about the visual pollution? What about this? What about that? I say, hey. What's the alternative, right? So I look at this, I'm beginning to look at this as an alternative to the urban freeway. Because urban regions need, something for 10+ mile driving, and that's the freeway. We don't drive 20 miles on surface streets. And, and if it's going to produce a benefit, to me, it has to be that. Cities give up like 30% of their land to roads and parking. And so it has to be that. But an urban freeway, 1 lane of urban freeway moves 3,300 people an hour, right? So that's a pretty high transport capacity. Now, commercial aviation, if you consider 300-seater aircraft separated by 5 miles at 500 miles an hour, that's actually 30,000 people an hour. So 1 lane of airway up in the national airspace system is actually 10 times, its transport capacity is 10 times higher than the urban freeway, right? But so I think this is a problem. So I'm actually interested in this problem. 10-seater, I want to see if 10-seater Cessnas can take off from a runway every minute, or 6-seater Cessnas can take off every 15 seconds. I've been talking to Omar Savash about the wake turbulence. And apparently, I don't know, I talked to this FAA test pilot who said to me, go to Palo Alto Airport, stand there with a stopwatch on Sunday morning, there's Cessna's taking off every 15 seconds. Don't worry about it. There is no wake turbulence. And apparently it's something to do with the Reynolds number, which changes, based on large aircraft and small aircraft and stuff like that, right? But I'm much shakier than you on all this. Okay, so to me, having thought all this through, to me, if I want to think about 10%, if I want to think about this as a way of changing America's land values, as a way of opening more land for housing, as a way of making like a train in an urban region, then to me, the regional airports are much more important. They have more transformative potential than UAM. We can think of high throughput operations at regional airports. The problem, of course, is the regional airports are deserts. There's nothing there, right? They're another set of playgrounds for the rich that cities are looking at and saying, why don't I somehow take these airports over and convert them into affordable housing? Right. So, and then, you know, a whole bunch of other people, the general aviation people go, America's losing its airport heritage. How could you do this? So, but the problem is there's nothing there except for a road and a parking lot that drives into it at this place that, right? So this is going to happen, you know, through some very long range planning process. So I do feel that, you know, there's some more math I've done, which I haven't put in here, but I do feel that, you know, you look at the Blade numbers, you look at the Joby numbers, Blade can make, according to me, Joby can make a revenue, or at least the market, that 1% market is worth, can be about $1 billion a day in a region like, $1 billion a year in a region like the Bay Area. So you think of 30 regions like that worldwide, it's a 30 billion market, right? There's about 4 billion of capital that was on my slide that has flowed into these companies. And you add other companies, there's another billion here or there. 5 billion of capital for a 30 billion market kind of makes sense, right? But for the rest of us, it is a business, but I don't see how it's transformative, right? So as a public university professor, I'm not particularly interested in it. But anyway, I'll stop there.
Questions, Dawn?
So I'll ask a question about the regional airports, because yes, they've stopped the service to all the regional airports in the outstate of Michigan. And there's not a lot there, but they're in beautiful places. So could people take one of these urban mobilities to fly from, say, I don't know, Kalamazoo or Houghton to Ann Arbor or Detroit and work? Would it be make sense for commuting?
You know, I think, you know,
I don't know how fast these things go.
so Joby says 165 miles an hour. And they have a range of 150 miles, right? The hydrogen powered people haven't yet put in their, you know, their operating numbers, right? But I think 150 miles is, where does that get you from here? How far is Mackinac from here?
Further than 100.
Further than 100, it's been a while since I've driven there.
Maybe Kalamazoo.
Yeah, so I do think that the $3 a mile does change the operating economics, right? And I think the right thing to do is to use the regional airports, but one will have to tell the eVTOL companies that you don't need that VTOL part, which you put so much work into. But that's definitely a very good thought. And so that whole thing needs to be thought about, right? How to get the airlines to start putting their regional flights back in.
I think part of it, though, is that there were 2 flights a day, right? It wasn't a commute from one of these regional airports. It was a trip. It was a connection. So it wasn't thought of as a transport that you would go every day.
I see.
So anyway, just curious.
Yeah, it was a feeder to their longer haul flights. Yes. Jeff.
So you've shown us a lot of numbers, and this has been very interesting. It seems like a lot of your analysis here is predicated on the idea that individuals are just not going to buy into the idea of having a vertiport in their front yard, right? Like individually, people are not going to do this. It has to be, as you said, hub to hub, not point to point.
This is true.
How sure are you of that? Because I'd like to have one in my front yard. I mean, I think it would be neat. So don't you think that there's a market for that, of people who would actually, you know, want that type of, who would actually see that as a kind of a status symbol to have something like that at their house rather than having to take things up? Because my question, my reason for asking this
Yes.
is, this is a fundamental adoption barrier, having to have it be hub to hub. And if you could make this kind of transportation so that it was as easy as taking your car somewhere,
So
it changes the game.
So I want to say that, so, okay, let me actually clarify something. I said all this, and now I want to backpedal. I'm not a Luddite, right? I mean, in the sense that, it's really fun to build aircraft, right? And I don't think somebody who comes and says that I want to build a flying car should be saddled with all this stuff. So what social problem exactly are you going to solve? I mean, you want to build a flying car, man. That's so much fun. The control problems are fantastic. Build it. It's great. I mean, that's why colleges of engineering exist. And, I was just telling Pete, decided to build a personal aircraft, right? But getting back to where I was, right? I would say that if that's the 1%, I don't change my story. So there is a 1% who'll buy a flying car, who'll buy a personal air vehicle. I might buy one if I can afford it.
But you use the adoption of automobiles as an example, and certainly first automobiles ever that were adopted were not adopted uniformly across the population. They were adopted by people who could afford it.
And they didn't go very far. People used to.
Obviously, eventually they did. I mean,
people used to laugh at them, right? Say, why don't you get a horse instead of that car? But I think I still. So I feel that there might definitely be a business and a market, and it might be large enough to sustain some of these producers. Like Joby's saying, $1.3 million an aircraft, right? I'm sure the personal, the flying car will be cheaper than that. But it's not going to reach $50,000 without scale. And that was really fundamental to Henry Ford's success.
Perhaps given the late hour, we can thank the speaker again and further questions to come to the front.
Hi, Arun. This is my son.
Sure, we can put it on.
Cookies for general consumption?
Yeah, you can have a cookie. Let me introduce you to some people. We'll start with Don.
Yes.
This is my son, 17-year-old. Don and I worked at Berkeley together.
Yeah, Michigan's a very different place than the Bay Area, but there's not enough.
Yeah.
And people have big enough front yards.
For heliports.
So, not a problem. I was gonna say, your front yard's probably a lot bigger than his.
no, actually, it was a hypothetical. I live in a townhouse.
Oh,
You live in a townhouse.
but a lot of my friends have an acre or two.
Yeah.
It's not.
As I was thinking, like, how did people view the garage? It's first to think, like, somebody can come up with the idea, I'm gonna put a garage right in front of me. Probably your neighbors all said that's the ugliest thing. Your road, the property values and everything. Yeah, that would just, it seems really hard.
What people are willing to do, and people who live in the outskirts now. If they don't live in the city, they don't have
I think he is. He was.
Yeah, okay. Yeah.
backyard, I bet.
I think that, I've sort of got this personal preference in sort of wanting to solve transportation problems. But I should try to understand your question, because all of that is, all of the technology needs a pathway, right?
And I think if
To scale. And
if you live in the Bay Area, you can't think about putting home for it.
yeah,
But
exactly.
if you live in Saline or Mile, probably can't.
Yeah.
Right? I mean,
And my
if you're 10 miles to
thinking
Ann
actually is
Arbor.
right. My thinking is very Bay Area focused.
So really, in that case, you're not talking about point to point, but you are talking about point to hub, which
Point
takes,
to hub.
takes away one of, at
And
least
then
part of the
you
adoption.
land in
area.
Ann Arbor.